Hello to you. I'm Jesse R. Johnson. I'll be speaking to you today about gyroscopes, the principles of gyroscopes, and why they behave as they do. Gyroscopes are fascinating. They can be purchased for a small amount as toys with gimbal and string. There are 5 to 6 general aspects of gyros that's been difficult to decipher even after 250 years, even though we use them in so many things as controls. Books give descriptions but not underlying reasons for their behavior, and millions have studied gyros but don't give complete explanations. Explanations in this video are done from physical behavior and done using highly simplified illustrations in 5 areas. Basics 1, lift, that's number 2, precession 3, guide force number 4, and stability number 5. To begin, the fundamental physical principle. It takes force to overcome force, no matter how that force is oriented, distributed, constructed, or patternized. Now, hold on for a second. I'm going to move the camera. Now, let's begin, please. Now, the basics. These are the basics at the top. The basics. We'll start with number 1. Number 1, 2, 3, 4. We'll start with number 1. All gyro discs turn, rotate, or spin because there's more torque that's turning forth than the disc has resistance against. Number 2. Number 2 is here, lift. A rotating gyro lifts because there's more upward force for it to do so than the downward force to stop it. It lifts because of that. And the faster the spinning, the greater the lift power. We'll go to number 3. Number 3, a gyro precesses because there's more linear, straight line force than any opposing power to stop it. We'll go to number 4. A rotating gyro disc stabilizes because the spin momentum force of rotation is greater than any counterforce to take it out of its plane of rotation, spin momentum direction. This is the plane of rotation is here. In this case, it's Y and Z, plane of rotation, and it is spinning clockwise. Now, we will go to number 5. Hold on, please. We will go to number 5. Number 5 is here. Number 5. To slow or stop a gyro disc down takes more force than the rotational momentum produces. This is a finger. And this is the direction of spin. This is trying to stop it. It takes force to stop this disc from spinning. We'll go to number 6 now. To tilt a rotating or high spinning gyro disc from its plane of rotation. Its plane of rotation is this one, for this one. Its plane of rotation takes more force than the disc is giving in resistance at any point on the disc. Any point on the disc. Now we will go to number 7. When a disc is rotated, there's centripetal force made of the atoms of the disc along every radius line composing the atoms' forces of the disc, of which is greater as a whole than the forces to pull it apart. Here are the atoms on the disc's rim, and here are the radius lines to those atoms. And here are next, a spinning disc. A spinning disc. This disc is spinning. A spinning disc has two linear momentum components, and they are primary and atomic. Now we will go to number 8. When a gyro disc spin is 0, it has no force to move in any of the x, y, or z coordinate directions because both the disk force, which is 0, and the EFF, which is the Earth's field forces, is simultaneous along the single downward line vector of the force of the EFF, or Earth's field forces, because gravity does not exist. Now, we will go to illustrations B, lift. Illustration B is lift. Now, I'm going to say a few things. A gyro rotating disc lifts for 3 reasons. Number 1, primary linear momentum component force. 2, guide force. And 3, precession force. All rotating or spinning gyro discs have 2 linear momentum components. 1, primary linear momentum component. 2, atomic linear momentum component. And when a gyro disc is rotated to high speeds, such as 6,000 to 20,000 RPMs, its primary linear momentum component cannot be pulled down by the Earth's field forces, or EFF, because the primary linear momentum component is greater in force. Gravity does not exist, but the Earth's field forces do, and it allows all that is known on the Earth. Gravity does not. When a gyro disc is spinning, the primary linear momentum component, when a gyro disc is not spinning, the primary linear momentum component and the atomic linear momentum component and the Earth's field forces are simultaneous in one line as one. Therefore, the disc is as of dead mass. Now we'll begin with the illustration. Number 1. As the disc begins to spin, you watch this arrow here, it's beginning to spin, even just 1 RPM, revolutions per minute, even 1 RPM, its primary linear momentum component translates from 0%, from 0 degrees, from the EFF. The EFF is here, the EFF, Earth's field forces, which is a downward direction vector resistance field force based on density of an object. The faster the disk spins, the greater its momentum, and the greater the degrees become separate from simultaneous as one. It becomes separate. From being a single one line, it becomes separate. They separate. The PLMC starts to separate from the EFF. And then the PLMC and the EFF moves toward their maximums of separation of 90 degrees. The faster the spin, the greater the force against the EFF's downward force. The force of lift is produced by the PLMC having more in the linear momentum force direction than the downward direction field force of the EFF. The LMC, the linear momentum component, is proven in 2 ways. We'll go to number 2. Number 2, spin the disc to high rotation speed and put the disc by itself on its edge on the ground without a gimbal or any attachment, and it will roll away because of the PLMC. Put it on the ground and spin it first, put it on the ground, and it will roll away because of the PLMC, or the primary linear momentum component. It will roll away just like a car wheel. Now we'll go to number 3. The ALMC atom, an atom on the edges of the wheel, on the edges of the disc itself, the ALMC, or atomic linear momentum component, is every single atom the disc is made of when the disc is rotating, and every atom is under centripetal force. Each atom is moving at a 90-degree angle to its radius line. It is moving at a 90-degree angle to its radius. This is the radius line. It is moving at a 90-degree angle to its radius line, that atom that it's part of. Now, and it will move in a straight line direction if it's disattached. If this atom comes off, it will go in a straight line direction from its radius line at 90-degree angle. And it takes force to move an object out of a straight line momentum direction in any and all three coordinates of x, y, and z. Now we will go to number 4. Number 4 is this. Number 4 here, how fast is a gyro disc when it is spinning? How fast is it going in miles per hour, or mph? This is how to calculate the mph speed of any rotating gyro. As an example, let's say a disc is 24 inches in circumference and it is rotating at 12,000 RPMs, which is equal to 200 RPSs, revolutions per second. Now, every 1/200th of a second, it traces out a straight line of 24 inches. The circumference length equals the linear length or straight line length in every case. This becomes 200 times 24 inches, which equals 4,800 inches. 4,800 inches times 60 seconds, 1 minute that is, equals 288,000 inches. Now, 288,000 inches times 60 minutes, which equals 1 hour, equals 17,280,000 inches. And 17,280,000 inches divided by 12 inches, which is 1 foot, equals 1,440,000 feet. And 1,440,000 feet divided by 5,280 feet, that's 1 mile, that is, equals 272.7 miles per hour. And if you want kilometers, it becomes 272.7 times 1.6 equals 436.3 kilometers. But it's going 272.7 miles per hour. And it takes serious force to counter this type of speed in any x, y, or z direction. That's number 4. Now, we will go to illustration C. We will deal now with precession, which is C, precession. Now, a high speed rotating gyro disc precesses because it has a primary linear momentum component. A primary linear momentum component in the direction of rotation or in the direction of spin greater than any counterforce to halt it from doing so. We'll go to number 1 right here. Here's number 1. Stand in front of the disc. If a radius line is drawn along the y coordinate line with left on one side and right on the other side, then if a turning force pushes it to spin left, you're pushing it to spin left, you're pushing it to spin, oops, hold on, if a torque force pushes it to spin left, the gyro disc will spin counterclockwise. You're pushing it this way so it turns counterclockwise this way. And if you push it right to spin right this way, right is that way, left is that way, then it will spin clockwise. And precess, and if it spin counterclockwise, it will precess left. If it spins clockwise, it will precess to the right. Now, the PL PLMC, or the primary linear momentum component, is greater than the counter force to stop it. Hence, it moves linearly. If a torque force pushes it right, the gyro disc will spin clockwise and precess right because the PLMC is right directional. Now we'll go to number 2. When a gyro precesses, it has when a gyro precesses, the centripetal force is in the disc and not the gimbal or the bar or the rod or the disc is attached to. Now we'll go to number 3. When it precesses, it has 2 axes, axis 1 and axis number 2. It has 2 axes, a central axis here for the disc and a secondary axis here at the tip end of the bar, pole, rod, or gimbal, of which is the axis the bar or pole rotates around when precessing. Now we will go to number 4 in precession. Now, number 4, even though the centripetal force is only in the high-speed rotating disc, it's only in the high-speed rotating disc, the bar, the pole, the rod, the gimbal system must have a guide. It must have a guide force to precess or lift. It must have a guide force to precess or lift, which can be a tabletop, a small indentation in a surface for the tip of the bar or gimbal to simply touch. This is the reason the disc precesses around the bar or rod. The force is in the disc, and not in the gimbal or the bar it's attached to. The tip end of the gimbal or the bar has no centripetal force on, or better yet, microscopic amounts of centripetal force. Only the disc has the main centripetal force upwards of 99.9999% and so forth. That's number 4. We'll go to number 5. The shorter the circular distance that the system has to precess in, the faster the precession. If this disc starts to lift, such as here, it will precess faster because the distance is shorter. If it starts to lift more, it's in a shorter path. These are the precession paths, and it will be precessing fast until it reaches vertical. It will be standing straight up vertically, and the precession and the spin will be along a single line simultaneous. And this here is the little small guide tower. The guide tower, that's number 5. We'll go now to number 6. Number 6. Now, number 6. When a gyro precesses, it has a precession direction. It has a precession direction, a PLMC, a ALMC, a clockwise or counterclockwise direction, a lift direction, an EFF or Earth field forces vector pulling it downward, and an angle to the surface and the guide force right here, an angle to its precession line as it lifts and turns and so forth. And of course it must be on the surface right here. Now we'll go to number 7. As a gyro spins, each atom the gyro is made of has centripetal force direction, pulling it to the center of the disc, and along the same line along the same line a tension force. This is the tension force. Tension force going upward. A centripetal force going down toward the center. And here's the atom at right here. And that angle, that atom is always going to, if it's disattached, it will move at a 90-degree angle to the radius line. That's number 7 here. And it has a centripetal force direction pulling it to the center of the disk, and along the same line a tension force pulling it from the disk. And if the atom disattaches, it will go and fly off at a 90-degree angle to the radius line. Now, we will go to number 8. Number 8. When the rotation of the disk is 100% vertical. It is 90 degrees, in other words, to the tabletop. It is 100% vertical. It's precession. Here it is precessing. But when it gets to complete 100% verticality, its precession and its spin is simultaneous at 90 degrees. Its precession and its LMC, which is primary anatomic, become simultaneous as one. Now, we will go to number 9. Pardon me. Let's see. Now, as the gyro spins, each atom the gyro is made of has a centripetal force and pulling and so forth. And when the rotation of the disk is 100% vertical, its precession is simultaneous with the vertical y-coordinate line. Now we'll go to number 9. Number 9, whatsoever the circumference of a disk from 0 degrees to 360 degrees, it is equal to the same in a straight line. If this is 1 foot in circumference, then a straight line is 1 foot when it is translated into a straight line. If the circumference equals x, then the linear translation line equals x. Now, we shall go to illustration D, guide force. The guide force, D. Now, the guide force number 1. A guide force is when the end of the gyro's gimbal or bar, which is attached to the gyro's central axis, is put on and in contact with a surface, smooth or rough, or a very small indentation of some type. In this case, this is the guide force. The guide force is this small little guide tower. And also, it has 2 guide forces. This here is the precess axis. This here is the central disk axis for the disk. This here is the bar the disk is attached to. This here at the tip end of the bar here is a small little guide tower. This produces lift and it produces precession. Precession. A guide force number 1 is when the end of the gyro's gimbal or bar, which is attached to the gyro's central axis, is put on and in contact with a surface. Here's the surface right here, or this can be the surface right up in here. And smooth or rough, or a very small indentation of some type in a surface. This creates guide force. This guide force does not force the bar to create centripetal force, but keeps it from going astray. A spinning or rotating gyro disc needs a guide force to help it lift or to help it precess. The tip end of the gimbal or bar must be guided. with exceptional minimal force for lift and or precess. Otherwise, it will not do so. A gyro cannot lift or precess without a guide force. Number 2. We'll go to number 2 now. There are two forces. There are two guide forces. There are two guide forces, the gimbal or bar for the disc, and the surface of which the gimbal or bar is in contact with. It can be a small indentation in a table, or it can be a smooth surface itself, but it must be in contact with something in order for that guide force to be transmitted into it. Otherwise it will not lift, it will not precess. It must have a guide force, and the guide force comes in two forms. It comes in the bar or gimbal that the system is attached, the disc is attached to, or it comes in the form of a dent or some surface that the bar tip end of the bar is touching or in contact with. Now, we will go to illustration E, stability. Stability is this. When a gyro disc is rotated, it acquires stability because the rotation is momentum force. Momentum force, and it takes a force to force it out of its primary linear momentum component, its atomic linear momentum component of rotation in the x, y, or z direction of its plane of rotation. Number 1, here's number 1. There are 3 possible planes of rotation for a gyro disc or ring: YZ plane, YX plane, or XZ plane. Now, number 2. It takes a force to move a disc out of its plane of rotation because it has momentum force. This particular disc is in the XZ plane. The X, here's the Z plane, and the X plane. This is it takes a force to move it out of that plane. Now, we will go to number 3. Number 3.